Welcome to lecture number 13. In the previous lecture, I recalled the preferred triangulated structure on the global stable homotopy category that comes from the fact that we had a stable model structure around. The shift functor in this triangulated structure comes from the suspension functor smashing with the circle S1, which is a homotopical functor, and so it descends to the global homotopy category. The distinguished triangles, like in any stable model category, come from mapping cone sequences on the level of the model. So in this case, mapping cone sequences associated with morphisms of orthogonal spectra. And then a general distinguished triangle is one that's isomorphic to such a mapping cone sequence. I also showed that the global stable homotopy category has a very convenient property in the world of triangulated categories. It is what it's called compactly generated. So there exists a set of compact weak generators. More precisely, the global classifying spaces of all compact Lie groups, or one choice of compact Lie group in every isomorphism class, these detect when an object is zero in the global stable homotopy category. That's a consequence of the fact that the global classifying space or its unreduced suspension spectrum represents the functor of equivariant homotopy groups. And this directly showed that these were compact objects, so mapping out of them takes infinite sums to direct sums, and that they generate because they see if an object is zero. Today I want to explain some interesting formal consequences of being compactly generated that are often summarized under the name of Brown representability. But before I get to that, I want to tell you another interesting fact, which comes from the fact that it's compactly generated. And this is a general proposition. So let T be a triangulated category with sums. And the emphasis is on infinite sums. Finite sums have to be there because it's additive. And let G be a set of compact objects. So objects such as mapping out of them takes infinite coproducts to sums. And then the following two conditions are equivalent. The first condition is that G is a set of weak generators. And hence the category is compactly generated, and this is equivalent to a different kind of generation, namely if you take the set of generators and you close it up, but now in a slightly different sense, you pass to the smallest localizing triangulated subcategory. So this means this is the intersection of all triangulated subcategories of T, which contain G generators and are also closed under infinite sums or arbitrary sums. They are then automatically closed under retracts. And the point is that the set of generators also generates in the sense that this is all of T, the entire category. And this will be useful later because in our situation, an example of this is that the global stable homotopy category is the localizing subcategory generated by the unreduced suspension spectra of the global classifying spaces of G, either for all compact Lie groups or one in every isomorphism class. So this is a useful fact, and here's a possible reference for it. You have to be a little bit careful because the compactness of this given set G, of the objects in this given set, is very important. If you don't assume compactness, then there's only one implication, and this is not, the two conditions are not in general equivalent. Now I want to get to Brown representability, which is a consequence of being compactly generated. The original formulation of Brown representability is due to Ed Brown, and this was published in a paper in the Annals in 1962. The original formulation was about contravariant functors on the homotopy category of based connected CW complexes, and it was a criterion for when such homotopy functors are representable. As an application of that, Brown also showed that generalized cohomology theories are representable by spectra. So this is the first instance of this connection between generalized cohomology theories and what we now study as spectra. Brown's arguments were later generalized by different people to various contexts. In the context of triangulated categories, a lot of the relevant work is due to Ammann and Niemann, and I'll give you some references a little bit later. To state the Brown representability theorem in the form that I know it, I have to introduce the notion of a homological and of a cohomological functor. So here it is. A functor E from a triangulated category T to abelian groups is homological if it takes distinguished triangles to exact sequences, so more precisely, if for every distinguished triangle A via F to B, via G to C, via H to A shifted by 1 in this triangulated category T, well, you get an exact sequence of abelian groups. The sequence EA via EF to EB via EG to EC, and then E of A of 1 via EH. This is now a sequence of abelian groups. Is exact. Because triangles can be rotated or shifted in both directions, you can then extend this to a long exact sequence of abelian groups. The dual concept is that of a cohomological functor. A functor E from T op to ab is cohomological if for every such triangle as above, as here, and then you just take the opposite sequence. Now it's contravariant, so now it's going to go from E of A shifted by 1 via E applied to the morphism H to EC via E applied to the morphism G, EB, E applied to the morphism F, DH. This is an exact sequence of abelian groups. And then again, because you can shift triangles in both directions, this really extends to a long exact sequence. A direct consequence of this kind of exactness is that these homological and cohomological functors are automatically additive. That's because direct sums always lead to exact sequences. So now I can formulate Brown representability in the form that is useful to us. We are considering a compactly generated triangulated category T. The first statement says that a cohomological functor that also takes sums in the triangulated category to products of abelian groups is representable. This is the formulation of Brown representability that is closest to the original result of Brown. The second statement is sort of dual. It says that every homological functor that takes products in T to products of abelian groups is representable in the other variable. The consequence that we're going to use is the existence of adjoints. The third property is that if you have an exact functor from the given triangulated category T to some other triangulated category, then this has a right adjoint if and only if it takes sums in T to sums in S. Clearly, if it has a right adjoint, it has to preserve sums, and the converse is really what matters to us. The third property is a formal consequence of the first. To get the adjoint functor on objects, you just apply the representability to the hom functor where you plug in the functor f in the first variable. To get the functoriality on morphisms, you apply the Yoneda lemma, which will also give you compatibility with composition. There's again the dual statement. An exact functor from our given triangulated category to some other triangulated category has a left adjoint if and only if it preserves products. Clearly, a functor that has a left adjoint has to preserve products, so again, the substance is in the converse. And again, property 4 is a formal consequence of property 2. All the triangulated categories that we care about come from stable model structures, and hence in particular from stable infinity categories. So you can wonder if there's an infinity categorical version of Brown representability, and in fact there is. The first observation is that a stable infinity category, whose homotopy category is compactly generated, is already what Lurie calls a presentable stable infinity category. Here's a reference to higher algebra. Presentability of an infinity category leads to representability and adjoint functor results. For example, if you have a contravariant functor from a presentable infinity category to the infinity category of spaces, then this functor is representable if and only if it takes colimits in the infinity category to limits of spaces. And this is the core ingredient to the adjoint functor theorem in this context, that a functor between infinity categories has a right adjoint if and only if it preserves colimits. Here are references to higher Tobus theory when you can find these results. The relevance for us is that whenever I'm going to apply the Brown representability theorem, there is really a higher infinity categorical representability or adjointness result in the background, and that's secretly a little bit stronger result, so that's something that's good to keep in mind. I want to now apply Brown representability to study the forgetful functor from the global stable homotopy category to the G-equivariant stable homotopy category for a fixed compact Lie group. So let G be a compact Lie group. And we have the forgetful functor, which goes from orthogonal spectra to orthogonal G-spectra, sending X to what I denoted X sub G earlier. So that's X endowed with a trivial G action. This functor takes global equivalences to pi star underlined isomorphism. By the very definition of global equivalences. And hence this functor descends to the homotopy categories. And this is going to be an exact functor of triangulated homotopy categories. And this time I want to introduce a separate piece of notation for this induced functor. I write it U for underlying and then G for the group under consideration. So this goes from the global stable homotopy category to the G-equivariant stable homotopy category, which is the localization of orthogonal G-spectra at the pi star underlined isomorphisms. Why is this induced functor an exact functor of triangulated categories? Well, that first of all means we have to endow it with an isomorphism where you first shift and then forget, or you forget and then shift. But of course, in both of these categories, the shift functor comes from suspension, which in both situations is fully homotopical. So the forgetful functor even commutes on the nose with the suspension functor. Similarly, the distinguished triangles in both of these categories arise from mapping cone sequences of morphisms of orthogonal spectra or orthogonal G-spectra. And of course, endowing something with a trivial G action preserves this construction. So that's why this is an exact functor of triangulated categories. And now comes the theorem that's essentially an application of Brown representability. So for every compact Lie group G, the functor UG has a left adjoint and a right adjoint. Moreover, for the trivial group, we have some special property. If G equal E is a trivial group, in other words, when we forget to the global stable homotopy category to the non-equivariant stable homotopy category, then both adjoints are fully faithful. Before I prove this, let me make one comment. So in the case of the trivial group, we're now in the following situation. We have the global stable homotopy category, this forgetful functor. I'm going to drop the notation for the trivial group. to the non-equivariant stable homotopy category. So this has a left adjoint that I will denote by L. It has a right adjoint that I will simply denote by R. And these are fully faithful, and this is a situation of what is called a recollement of triangulated categories. Often people denote in the recollement the extra piece of information of the kernel of, in this case, the forgetful functor. So this is the category of all orthogonal spectra, such that the non-equivariant stable homotopy groups vanish. So these are exactly those objects here that go to a zero object under the forgetful functor. And it's then a consequence of representability results that there are two further adjoints. This inclusion functor also has two adjoints, and this entire situation is what's called a recollement. Another comment before I enter the proof. So this is actually a prototypical situation of the comment I made a little bit earlier. I will prove these statements on the level of triangulated categories, but there's really an infinity categorical statement of the entire story in the background. You know, this forgetful functor is homotopical, so it descends to a functor of the infinity category of global spectra to the infinity category of genuine G-spectra. And as a functor of infinity categories, this functor has both adjoints. Moreover, if the group is trivial, then both of these adjoints are fully faithful, but now in the infinity categorical sense. The proof of the first claim is an application of Brown representability. So we have to verify the hypothesis of Brown representability. This triangulated category is compactly generated, so we have to check that in addition the forgetful functor preserves sums and products with the emphasis on infinite sums and infinite products. The case of coproducts is somewhat easier because coproducts in the global stable homotopy category and in the G-equivariant stable homotopy category are represented by wedges in complete generality without having to covariantly replace, and the forgetful functor clearly preserves wedges, and the functor sending x to the underlying G spectrum, meaning with a trivial action, preserves wedges. So this case is easy because all the constructions involved, the forgetful functor and coproducts in the two categories of models, are all fully homotopical. Strictly speaking, I didn't show this for the G-equivariant stable homotopy category, but the argument is completely analogous to the global stable homotopy category. If you believe that this all comes from a stable model structure also here, then you just have to observe that in addition here also coproducts or wedges of orthogonal G spectra are fully homotopical for pi star isomorphism in this case, and that's because equivariant homotopy groups take wedges to direct sums. So the forgetful functor, the derived forgetful functor, preserves arbitrary coproducts, and hence it has a right adjoint by Brown representability. The second half of the first statement is essentially dual, but it's a little bit more complicated because infinite products don't preserve global equivalences. Nevertheless, UG also preserves products, but this needs an argument that I want to explain in some detail. So first of all, in the global stable homotopy category, every object is isomorphic to a global omega spectrum, so it suffices to consider a family of global omega spectra. Let xi, I in I, be a family of global omega spectra. And then we can take the product this is again a global omega spectrum. And it represents the product in the global homotopy category. So we must show that if I take the product of these global omega spectra and endow this with a trivial G action, and this is a product of the family that I get by taking the individual spectra and endowing them with a trivial G action. And this must be a product in the G-equivariant stable homotopy category. So this is not completely automatic because of this slight complication that if I have a global omega spectrum and I endow it with a trivial action, I don't quite get a G omega spectrum. So in the standard stable model structures that gives rise to the G-equivariant stable homotopy category, the finite objects are all certain kinds of G omega spectra, and that means the omega spectrum condition has to hold starting from the trivial representation, starting at an arbitrary representation, whereas for global omega spectra we only have this starting at faithful representations. So it might seem that we have a problem here, but actually we don't have a problem. So how would we calculate the product in here? Well, we would have to fibrantly replace these objects and then take the product, and that means we have to replace each of these factors by a G omega spectrum. So choose pi star isomorphisms Fi from xi with a trivial G action to some orthogonal G spectra yi in orthogonal G spectra with yi a G an omega G spectrum, G omega spectrum. So one thing that will happen is that while these were all orthogonal spectra with trivial G action, this will typically have non-trivial G action. You cannot in general arrange that these come from global homotopy types, that these have trivial G actions again. And now the key point is that even though infinite products in general do not preserve pi star isomorphisms, they do in this special situation. So the claim is that the map product of the Fi's going from the product of the xi's to the product of the yi's is again a pi star underlined isomorphism of orthogonal G spectra. And the proof of this is an instance of a philosophy that I also mentioned in one of the earlier lectures, that even though global omega spectra, when you let G act trivial, don't quite give full G omega spectra, they are sort of faithful G omega spectra, and this is often good enough in particular situations. So let us choose a faithful G representation, or first choose a closed subgroup. So let H be a closed subgroup of G, and V a faithful H representation, because we want to show it's an isomorphism on H equivariant homotopy groups. So then I want to look at the canonical map. I take H equivariant map from the one-point compactification of the xi's evaluated at G, and this going to pi 0h of the product of the xi's, and I claim this is an isomorphism. So why is this the case? Well, here it doesn't matter how I put the parenthesis. The product of the xi's at V is the same as the product of the xi's and then evaluated at V. And that is a global omega spectrum again. And that means in the colimit system that defines this pi 0h equivariant of the product, we will have isomorphisms starting at any faithful representation V and larger, because this is the global omega spectrum property, that starting at a faithful representation we get weak equivalences in the adjoint structure maps, equivariant weak equivalences. So this map is actually an isomorphism. Now I consider the following commutative square. G-equivariant based maps from the V-sphere to the product I in I of the values of the global omega spectra at V, H-equivariant based maps, and I just argued that the canonical map to the colimit of this system, so to pi 0 of the product I in I of the xi is bijective. So here I can pull the product out and I get a bijection to the product over I and I based continuous H maps from SV into xi of v. So why can I pull this out? Well, this is homotopy classes of maps. Continuous maps into a product is the product of continuous maps, and homotopies are also continuous maps, just from some different space. So you apply the universal property of a product to maps and to homotopies, and then you get that this is a bijection. So this maps to the product over I in I of the 0 H-equivariant homotopy group xi. And this map is a bijection because for each individual factor, so for each fixed I, we have a global omega spectrum. So that's another instance of the example on the last whiteboard, that we get a bijection for each individual I and hence for the product. And then we conclude, because the other three maps in this commutative diagram are bijections, that also the canonical morphism from the product inside to the product outside is a bijection. So while infinite products of orthogonal spectra don't in general commute with equivariant homotopy groups, they do commute in this particular situation when all the factors are global omega spectra. Now we can conclude the proof. So now we look at another commutative diagram. We look at pi 0 h of the product I in I xi, the canonical map where the product goes outside, product I in I, pi 0 h equivariant of xi. And I wanted to show that the product of the G omega spectrum replacement maps, so product of the fi's, this goes to pi 0 h equivariant to the product I and I of the yi's. I wanted to show that this product map induces an isomorphism on all equivariant homotopy groups. Here I also pull the product out, I and I, pi 0 h equivariant of yi. And here I have the product of the pi 0 h of fi. Each fi was a pi star underlined isomorphism, so this map is a bijection down here. This map is an isomorphism because we have G omega spectra, these are the finite objects, so here the product also commutes. And we conclude that this third map is also an isomorphism up here, and that was the claim. Well, I really argued only for dimension 0, but the argument in a general integer dimension is exactly the same. So I have shown the claim that the product of the fi's is pi star G isomorphism, and hence an isomorphism in the G-equivariant stable homotopy category. So this is UG applied to the product, and this is the product after you've taken the UGs, so this concludes the proof that UG preserves products. So by this other statement in the Brown representability, I can conclude that UG also has a left adjoint. I still owe the proof of the second claim. So now we restrict to the special case where G is the trivial group. And then we have the forgetful functor. I will now drop the notation sub G to simplify the notation, which goes from the global stable homotopy category to the non-equivariant stable homotopy category. We already know that we have a left adjoint and a right adjoint. And now we have to show that these two adjoints are fully faithful. I will start with a special claim, which is saying that the left adjoint takes the non-equivariant sphere spectrum to the global sphere spectrum. So here's the more precise statement. So the identity of the sphere spectrum, which is the same as the underlying non-equivariant spectrum of the sphere spectrum. This is a right adjoint here, so I can adjoin it. So the identity in the non-equivariant stable homotopy category is adjoint to a morphism from the left adjoint applied to the sphere spectrum to the sphere spectrum. And this is in the global homotopy category. And I claim that this adjoint morphism is actually an isomorphism. So this is the precise formulation that the left adjoint takes the non-equivariant sphere spectrum to the global sphere spectrum. We're going to test that it's an isomorphism by mapping into an arbitrary orthogonal spectrum. So let X be any orthogonal spectrum. And then we're going to calculate morphisms in the global stable homotopy category into this object, from this object, and from this object. So first of all, if I take morphisms in the global stable homotopy category, from the left adjoint applied to the sphere spectrum into X, so this by adjointness is morphisms in the non-equivariant stable homotopy category, it's really the adjunction isomorphism, to the sphere spectrum and then the underlying spectrum of X. And the sphere spectrum in the non-equivariant stable homotopy category represents the zeroth non-equivariant homotopy group. On the other hand, if we calculate morphisms in the global stable homotopy category from the global sphere spectrum into the X, this is also the zeroth equivariant homotopy group of X by evaluation at the stable tautological class. And this is because the sphere spectrum is the unreduced suspension spectrum of a global classifying space of the triple group. And now I leave it to you to check that this particular morphism actually, precomposition with this particular morphism actually induces this bijection. So once we know that, since we've tested against an arbitrary orthogonal spectrum, we conclude that this morphism is an isomorphism in the global stable homotopy category. The next partial step involves the verification that the unit of the adjunction is always a non-equivariant isomorphism. So the next claim is, for every orthogonal spectrum A, now considered as a non-equivariant stable homotopy type, the unit of the adjunction for L and U, so this is a morphism from A to U of L of A, and I claim that this is an isomorphism in the non-equivariant stable homotopy category. How do we see this? Well, we use the fact that the non-equivariant stable homotopy category is compactly generated by the sphere spectrum, and hence also generated in this sense of localizing subcategory by the sphere spectrum. So we observe that the class of all X in the non-equivariant stable homotopy category, for which this is an isomorphism, is a localizing subcategory. Of the non-equivariant stable homotopy category. Why is it? Well, first of all, we have to show it's a triangulated subcategory. That means we have to check if in a distinguished triangle two of the objects are in it, then so is the third. But the identity is an exact functor. L and U are exact functors, so this becomes an application of the 5 lemma, 2 out of 3. Then we have to check that this subcategory is closed under arbitrary coproducts, arbitrary sums. And that is true because both the left adjoint, well, as a left adjoint, it always preserves all coproducts, but also the U, this is something we just showed before, preserves coproducts. So this functor and this functor, they both preserve coproducts. We have a natural morphism between them, and hence the class of objects for which it is an isomorphism is closed under coproducts. So now we have a localizing subcategory which contains the sphere spectrum, since this class contains the sphere spectrum. You know, if we apply the forgetful functor to this isomorphism, then by the triangle inequality we get it's an isomorphism, and it's also inverse to the adjunction unit. So this shows that S is in this class. We must have, the class must be everything. This must be all of the non-equivariant stable homotopy category. We've just seen that for every non-equivariant stable homotopy type, the unit of the adjunction is an isomorphism in the non-equivariant stable homotopy category. Or put differently, the left adjoint is also right inverse to the forgetful functor. And it's a formal consequences of this that the left adjoint is fully faithful, and here's how the argument goes. So now we consider two non-equivariant spectra, A and X, and then we apply the left adjoint. So this gets us to morphisms in the global stable homotopy category from LA to LX. By the adjunction, this bijects with morphisms in the non-equivariant stable homotopy category from A into ULX. And the triangle inequality says that this triangle commutes if we here put the induced morphism from A and then the adjunction unit eta x. So we just showed this adjunction unit is an isomorphism, so we get an isomorphism here, the adjunction bijection, so L is fully faithful. Another formal argument now shows that the right adjoint is fully faithful, and here's how we argue. So we consider morphisms in the non-equivariant stable homotopy category from ULA into some spectrum Y. Then here I apply morphisms in the non-equivariant stable homotopy category out of the unit for the LU adjunction into Y. This is a bijection because this unit of the adjunction is an isomorphism. This gets us to morphisms in the non-equivariant stable homotopy category from A into Y. Here I can use the adjunction isomorphism for the other adjunction, for the one between U and its right adjoint. So this gets us to morphisms in the global stable homotopy category from LA into RY. And then I can apply another adjunction, but this is now the adjunction between L and U. This gives us, and so I first pull the U over and then I pull the L over. So this gives us a bijection to morphisms in the non-equivariant stable homotopy category. And here we have A, U, R, Y. And then I leave it for you to check that this diagram will commute if I here put morphisms in the non-equivariant stable homotopy category out of A and then the co-unit for the adjunction, the other one for the UR adjunction that this diagram commutes. And then again we have a commutative square. 3 out of the 4 maps are bijective, so we conclude that this map is also a bijection. Because R was arbitrary, we've tested out of an arbitrary object into a morphism. This morphism must be an isomorphism. So the co-unit of the other adjunction, of the UR adjunction, from URY to Y is an isomorphism in the non-equivariant stable homotopy category. And then from here, the dual argument to the one up here shows that the functor R is fully faithful. Let me give you a little bit more information about the left adjoint to the forgetful functor so you get a better feeling of what it looks like. The left adjoint is an exact functor and it preserves infinite coproducts. So it's determined by what it does on the compact generators of this compactly generated triangulated category, which were the suspension spectra of all the G mod H's for H a closed subgroup of G. And I will tell you a little bit more generally what this L looks like on the suspension spectrum of a cofibrant G space. So let A be a cofibrant G space. So for example, a GCW complex. And now we choose a faithful G representation. Now I'm going to construct a candidate map that I will later show as an isomorphism. So we start with a map of base G spaces. So the G map from the V sphere smash A with a disjoint base point added to the V sphere smash linear isometric embeddings from V into V cross over G with A. So here I'm co-equalizing the right G action coming from the action on the source with a given left G action on A, and then I want a disjoint base point. And then I observe that this is really the value of some orthogonal spectrum, namely the unreduced suspension spectrum of the orthogonal space, which is kind of a relative version of the global classifying space. It's the value of this unreduced suspension spectrum at D. So if A was a single point, then this would just be dividing out the G action, and this would be a global classifying space of the group G. So it's a little bit more general version of this. So this is a G map. And now this is adjoint to a morphism of orthogonal G spectra. Mainly from the suspension spectrum with a disjoint base point added. So first we're going to adjoin the SV over and then we're going to shift it because it's not the value at 0 but the value at v, so this lands in shift v omega v of the underlying G spectrum of the suspension spectrum of L of v blank cross over G with A. So this is an orthogonal spectrum. Altogether it has trivial G action, but then when we loop by v and we shift by v, we get an honest orthogonal G spectrum with non-trivial G actions. And now we have this morphism of orthogonal G spectra, and then this gives in the homotopy category, in the G-equivariant stable homotopy category, we get the morphism. First we apply the localization functor to this points at level morphism. I'm not going to introduce special notation for this, of UG of sigma infinity plus L of v blank over G with A. And then in the world of orthogonal G spectra, there are these lambda maps. So this is the lambda V map for this orthogonal G spectrum. The lambda maps are pi star underlined isomorphisms. Now I've passed to the G-equivariant stable homotopy category. So in there it's an isomorphism. And here we get to UG of sigma infinity plus L of V cross over GA. So this is a morphism in the G-equivariant stable homotopy category. Here's the underlying G spectrum of some orthogonal spectrum. So this is adjoint to a morphism of global spectra. This is adjoint, the composite, to a morphism in the global stable homotopy category that I want to give a name, phi. So I apply the LG to the suspension spectrum plus, and this gets us to sigma infinity plus L of v blank cross over GA. Now the claim is that this is an isomorphism. Phi is an isomorphism in the global stable homotopy category. So the short and slightly imprecise version of this is that the left adjoint takes the suspension spectrum of a G space A to the suspension spectrum of this global space, of this orthogonal space, and the precise version is more precise because it really gives you the map that does the job, not just that they are isomorphic. The proof that this morphism phi is an isomorphism in the global stable homotopy category will proceed by showing that if I map into an arbitrary object in the global stable homotopy category, I get a bijection. So we let X be a global omega spectrum. So after all, in the global stable homotopy category, every object is isomorphic to a global omega spectrum. And then if we take the underlying G spectrum of X, we loop it by V, and we shift it by V, then this is a G omega spectrum. So this is a fix to this problem that the underlying G spectrum of a global omega spectrum is not a full G omega spectrum, but we have this faithful representation V, and because we shift by V, this spectrum, where you first loop and then shift, will only have values that are V plus something else, and these are all faithful representations. So this is kind of the trick to cure the defect that XG is not a G omega spectrum. But after this slight manipulation, it will be. And moreover, we have the lambda map, which already occurred before, which goes from the underlying G spectrum of X, which is just XG, to shift V omega V of UG of X. This is a pi star underlined isomorphism of orthogonal G spectra. So it's an isomorphism in the G-equivariant stable homotopy category. So now we consider the following diagram, which I claim commutes. So here we start with homotopy classes of maps unstable from SV smash A plus into the value of X at V, and then G-equivariant based homotopy classes of maps. Now we're going to compare this to other things. So here I have morphisms in the category of orthogonal spectra. from the unreduced suspension spectrum of L V G blank cross over G A into X, and then modulo homotopy of morphisms of orthogonal spectra. So this map is a bijection, and this is just the adjunction, because spectrum morphisms out of this are the same as unstable G-equivariant morphisms from here to here. This is the representability, it's the enriched unit dilemma, if you want. Now there's a little thing for you to check, so this is maybe an exercise, that this orthogonal spectrum sigma infinity plus L of V blank cross over GA is a flat orthogonal spectrum. So this will use that A was assumed to be a covariant G-space. This is a global omega spectrum, this is a flat spectrum, so the global model structure tells us that the localization functor is a bijection to morphisms in the global stable homotopy category between the same objects. So this is one identification. This works in the global stable homotopy category, and now we're making an analogous comparison in the G-equivariant stable homotopy category. So here I put morphisms of orthogonal G spectra from the suspension spectrum of A into omega V shift V of xg modulo homotopy, and another adjunction, this time for orthogonal spectra with a G action, morphisms of G-equivariant spaces from here to here. You can first adjoin the suspension coordinate over, and then you have omega V, and then you pass to the suspension spectrum. So this is another adjunction that gives us this bijection. Here, we're in the situation that this, because A was a cofibrant G space, this will be cofibrant in the projective model structure of orthogonal G spectra, the one that's used by Mandel and May. This is a G omega spectrum, so this is actually a fibrant object in the stable model structure of orthogonal G spectra. So the localization functor, the analog of this localization functor, but for orthogonal G spectra, gives us a bijection to morphisms in the G-equivariant stable homotopy category between the same objects. So strictly speaking, I'm using something here that I haven't fully discussed. I've only indicated these stable model structures on orthogonal G spectra, and now I'm actually using them. So this is another bijection. Then we have this lambda map, and this lambda map is a pi star isomorphism, so it induces an isomorphism in the G-equivariant stable homotopy category between sigma infinity plus A and xg, but here I can write uj of x, that's just a different name for this. Now I'm using the adjunction here, so this is by the adjunction between lg and ug, we get a bijection to morphisms in the global stable homotopy category from lg of sigma infinity plus a into x. And then another thing I leave for you to check is that the morphism in this direction, which is this phi morphism in the first variable mapped into x, makes everything commute. And again, we're in the favorable situation. We have a commutative diagram where all the remaining maps are bijections, so we conclude that this is a bijection. And since we tested against an arbitrary object in the global stable homotopy category, at least up to isomorphism, we tested against global omega spectra, we can conclude that this morphism is indeed an isomorphism in the global stable homotopy category. Let me point out an interesting special case of the isomorphism that we've just constructed. For this we consider a closed subgroup of the given convective group G. So then I can consider the left adjoint applied to the unreduced suspension spectrum of homogeneous space G mod H, and I just constructed an isomorphism to the unreduced suspension spectrum with a disjoint base point added of LV blank cross over G mod H. But of course this is isomorphic to the unreduced suspension spectrum of LV comma blank modulo H. And now V was a faithful representation of the bigger group G, but then it's of course also a faithful representation of the smaller group H. So this is the unreduced suspension spectrum of a global classifying space of H. So this is something worth remembering. The left adjoint to the forgetful functor to the G-equivariant stable homotopy category takes this generator here, the suspension spectrum of G mod H, to the global classifying space of H. Because the left adjoint is an exact functor and it preserves infinite coproducts, it is in some sense essentially determined on what it does on the generator, so this gives us a lot of control about what the left adjoint does. It does not mean, however, that you are given a general orthogonal G spectrum that's not a suspension spectrum. It doesn't necessarily mean there's a good way of working out explicitly what the left adjoint does to this. I can also use this isomorphism to show you that the left adjoint is definitely not fully faithful in general. So LG is not fully faithful unless, of course, we already showed it is fully faithful when G is trivial, but now I can show you that it's not fully faithful when G is not trivial. So how can we see this? So first of all, let's calculate G-equivariant morphisms in the G-equivariant stable homotopy category from the G-equivariant sphere spectrum to the G-equivariant sphere spectrum. Well, this object in this category represents the G-equivariant homotopy groups. So this is isomorphic to pi 0 G-equivariant of the G-equivariant sphere spectrum, and this is isomorphic to the Burnside ring. G. So when G is finite, it's isomorphic to the only group of isomorphism classes of finite G sets and the disjoint union. Well, and in general, it's what's called the Burnside ring. It sort of is what it is, but we know it's free abelian generated by the transfers from closed subgroups with finite value. On the other hand, we also know what LG applied to SG is, because this is really LG applied to the unreduced suspension spectrum of G mod G. So by this isomorphism above, this is a global classifying space of G, sigma infinity plus B global G. So let's calculate what morphisms in the global homotopy category are. Sigma infinity plus B global G to sigma infinity plus B global G. Well, by an earlier result, this is really the morphisms in the global Burnside category from G to G, and this is what's sometimes called the double Burnside ring. So while this is a free abelian group generated by transfers from certain closed subgroups, this is a larger and general free abelian group generated by transfers after restrictions. And if you go carefully through as to what under these identifications, what the effect of the left adjoint homomorphisms is, then you will find out that it's the homomorphism from the Burnside ring to the double Burnside ring, which sends the transfer from H to G to the transfer from H to G after restriction from G to H. And this map is not surjective unless G is trivial. So this is really, so to speak, the effect of the left adjoint after making these identifications. And since it's not surjective, the left adjoint is not full. And then, if you extend to more complicated object, you will also soon get at an example of an orthogonal G spectrum where it's not faithful. I don't want to discuss the right adjoint to the forgetful functor in detail. In the next lecture, I will investigate the situation for the trivial group more closely, and there I will show that the right adjoint is a global version of the Borel construction. In the G-equivariant context, you can think of the right adjoint as kind of a relative version of a Borel construction, but I don't want to go into detail about this. This is all I wanted to explain today, so I thank you for your attention.